6.2 Integration by Substitution, Part 2. Your objective for this lesson is to integrate using u substitution. Okay, so all previous examples that we've seen from Part 1 were instances of this general method, which works because big F of g of x is the antiderivative of f of g of x times g prime of x. When big F is the antiderivative of f. Now, example 6, still integrating with u substitution. Now, we're trying to evaluate the function, or the integral, x squared plus 2x minus 3, the whole thing squared, times x plus 1 dx. This looks like a complete mess. So u substitution will definitely help. I'm going to make this part u. The reason for doing that is when I take the derivative, I know I'm going to have fewer terms, and it might end up looking something like this. So u equals x squared plus 2x minus 3, and du is 2x plus 2 dx. Okay. And comparing this that I have here to this, I'm almost there. It looks like I've multiplied by 2 though. So why don't I factor that 2 out? Okay, now you can see it even more clearly. So I do have the x plus 1 dx in both the original problem and what I have down here. But I still have that extra 2, so I'm going to divide both sides by 2 to move it. So we have 1/2 du equals x plus 1 dx. Now I can rewrite my problem. So I have the integral of u squared times 1/2 du. Can move my 1/2 out to the front. So we have 1/2 integral u squared du. Now to evaluate this, I'm going to say 1/3 u cubed plus c. So I end up with 1/6 u cubed plus c. And all I need to do now is plug my u back in, which is x squared plus 2x minus 3. And here is my answer. That is so much easier than trying to actually work with that. Example 7. Evaluate the integral sine to the 4th of cosine x dx. Okay, so here I'm going to say, oh gosh, there should be an x in here. Hold on just a second. Okay, that's better. So sine to the 4th x cosine x dx. And here I am going to make sine my u. So u equals sine x. I'm doing that because cosine x is the derivative of sine x, and we have sine to the 4th x. So there's a little bit more going on here. And du is going to be cosine x dx, which is exactly what I have there, so I don't have to really play with that anymore. So I have the integral now of u to the 4th du, which becomes 1/5 u to the 5th plus c. And then I can plug my sine back in. And I'm going to write this as sine to the 5th x over 5 plus c. You could write this way, or you could write it as sine x the whole thing to the 5th over 5 plus c. So either of these would work. Do not write your answer like sine x to the 5th over 5, because that's sine of x to the 5th. So that's different. This is okay. This is okay. This is not okay. Okay, substitution indefinite integrals. So far we've looked at substituting for indefinite integrals only, but you can also use this to solve definite integrals. That's what we're going to look at right now. Example 8, evaluate the integral tan x secant squared x dx from 0 to pi over 4. So our first step, as before, is to figure out what u is and substitute. I'm going to say that tan x is u because the derivative of tan x is secant squared x, which is this part right here. So we're integrating u du. The only tricky part here is you need to figure out new bounds. This integral was talking about x. We were integrating x. Now we're integrating u, so we need bounds that deal with u. So I'm going to evaluate these two bounds, so the lower bound and the upper bound, at u. So u of 0 is tan of 0, which is 0. U of pi over 4 is tan of pi over 4, which is 1. So I'm integrating u from 0 to 1. Okay, and now I can evaluate the integral. This becomes 1/2 u squared. And there's no plus c because it is a definite integral, but we are evaluating from 0 to 1. And this is going to be 1/2 of 1 squared minus 1/2 of 0 squared. I know this is a big fat 0, and this is 1/2 times 1, which is just 1/2. So that's my answer, 1/2. Example 9, last example for this lesson. Solve the differential equation dy dx equals 2x times 1 plus y squared times e to the x squared. Okay, and we are going to solve this by separating the variables. You'll see that I have both an x and a y on this side. There's another x here. I have dy and dx. So I want to get all my y's and my dy's on one side, all my x's and dx's on the other side. So I'm going to divide by 1 plus y squared, which is the same as multiplying by 1 over y squared. And I'm going to, that'll cancel this, and I'm going to multiply by dx. That'll cancel these. So I have dy over 1 plus y squared equals dx e to the x squared dx on the other side. From here, I can integrate both sides. And I end up with, well, this 1 plus y squared on the bottom tips me off that this is really arctan of y plus c. Okay, and over here I'm going to substitute. Instead of e to the x squared, I'm going to make that e to the u. So u equals x squared. And then du is 2x dx. And look, we have 2x dx. So this is really the integral of u du. When I integrate that, I get 1/2 u squared plus c. And I'm not going to rewrite the c on this side because this c represents our combined constants of integration. So basically we only need one constant here. We are trying to get y by itself, so it makes sense that the c goes with the x terms. Okay. Now I'm going to substitute back in. So instead of, hold on a second. That shouldn't be a u. That should be e to the u. So we had e to the u du here. And when I integrate e to the u, I get itself. There we go. So now I'm going to substitute back in. So I have e to the x squared plus c. Okay. But I want to get y by itself, so I'm going to tan both sides. So the arctan and tan will cancel. And y equals tan of e to the x plus c. That is my answer. That wraps up 6.2.